Welcome everyone. This is our 113th live stream geometry. So I couldn't make it last week, but now I am back and we have 4 people here with us from Germany, Vietnam, and Malaysia. And I'm from the US. And today we're going to go through 3 problems from a mock geometry contest from India and another 3 problems from a geometry marathon on AOPS. So if you want to join us in the future, feel free to email me at mgreenb801@gmail.com. It's in the description of my video, and we meet every Sunday at 8 a.m. US Central Time. All right, so I'm going to share my screen. So here is the first problem. Let me try to maximize. I always have trouble maximizing. There's some keyboard shortcut. I think it might be like F12 or whoops, not that. F9 maybe, F11, that's it. Okay. So I tried to click it and it didn't work, but the keyboard shortcut works for whatever reason. All right, so we have a circle and we have 2 points P and R on it. And O is an arbitrary point on the perpendicular bisector. So let's draw P and R. We can rename them. And O is an arbitrary point on the perpendicular bisector. So we could just let this be O right here. And not only that, we have a circle, an arbitrary circle of arbitrary radius with center O. So the radius doesn't matter, but we let OP and OR meet the circle at M and N. And then we draw the tangents at M and N, and they meet the big circle at Q and S. But what breaks the symmetry here is that Q and S are on opposite sides of segment PR. So kind of like this. Let me try to, maybe I could draw this a little nicer. Looks like we have one more person joining. So the tangent at M meets it at Q. And the tangent at N meets it at S, so that P, Q, R, and S are in that order. And let's see who just joined. Hey, Georgie, thanks for joining. So maybe it might just help to draw the symmetric points like that. So QD is parallel to PR by symmetry, and so is ES. But PQ and RS intersect at K. So here's where the diagram gets less symmetric. They meet at K. It almost looks like K, D, and E are collinear. Maybe not actually. That's K. And we want to show, if we take the midpoint of PQ and RS, then we want to show that FG is perpendicular to OK. All right, so yeah, K, D, and E are not linear. I wonder if KFG is isosceles. It almost looks true, but I'm not sure. Let's check it out. No, is it really true that KM equals KG? No, that's not true. Okay, so let's delete the circle. So we want to show FG is perpendicular to OK. Obviously, OF is perpendicular to PQ, and whoops, sorry, AF is perpendicular, and so is AG. So, oops, looks like we have someone else joining us. Yeah, it's really interesting. Yeah, this circle can be any radius it wants, and the problem's still true. So even if we make it a really small or a larger circle, it's still true. So KFAG is cyclic because it has two right angles. And what else do we know? I don't think there's any other kind of point, so I'll just remember that. So since KFAG is cyclic, we can kind of find the angle that FG makes with AK, but not necessarily with OK. Maybe we should let EM and NS meet at a point. That might make things easier. So yeah, let's draw this point right here. Call it H. I bet that point will be useful. Oops. Great. Is HK parallel to PR and no, not necessarily. I don't think so, at least. Yeah. And yeah, these kind of look like they concur, but it's not true either. But HMON is cyclic. We have two cyclic quadrilaterals. And KFAG. All right. So O and A are isogonal with respect to PKS. Interesting. I think that definitely does help. Then I wonder if the problem just reduces to an angle chase, actually. How did you find that out? So AKG is AFG, right? So what I was thinking is we could find the angle that AK makes with FG, and then we could find the angle that OK makes with AK, And then combining those two, we get the angle that OK makes with FG. So if we could show that's 90 degrees, that would solve the problem. So angle AKG, or if I draw this point, for example, angle KIF is IKG plus KGI, and IKG is AFG, and IGK is IAF. So those angles look like they might be easier to compute. But yeah, that's interesting that, okay, so those are isogonal. Do you remember how you figured that out? Or is the problem equivalent to showing they're isogonal? Oh, it's equivalent. Okay.
It's equivalent because in triangle FKG, KO is the altitude and KA is the diameter of the circumcircle. So if KO is the altitude, then they are isogonal.
All right. Interesting. And angle AKG is AFG. So same as saying this angle equals this angle. Is EHKS cyclic? No. I wonder if H and K lie on some circle. So yeah, another way of saying it is that I think it's the same as saying there's a spiral similarity that takes KJF to KGA. So if that were true, yeah, then it would also take KFA to KJG. I wonder, does O correspond to S in that spiral similarity? I could check that. Here's one way to check that. If that were the case, angle FOK would be angle ASK. So that is 64.99. Okay, so it's not true that S and O correspond. think about this. Yeah, we have a lot of right angles here. We prove it for a certain special case. We vary the, if O equals A, is it obvious? Let's see, if O equals A, then we have two tangents to the circle, Q and S. And maybe that'll give us some insight. So if O and A are the same point, then that would mean PQ and RS are the same length. Is AHQS cyclic? Let's check. Yes, it is. How did you see that? Let's think. This is an angle bisector. Oh yeah, because HA bisects QHS, so that has to be true. Oh, but yeah, it's easy to see because yeah, HA is an angle bisector of QHS. Yeah. So if that's cyclic, then HRA, we know HRAP is cyclic. Can we use, oh wait, that's not true. Oh yeah, it's not true necessarily. So yeah, HDEA would be cyclic. But yeah, that's good to know. So that means angle ASH is AQE. Okay, let me go back to trying to prove it when O equals A. In that situation, so then we'd have AF and AG are both perpendicular to PQ and RS. So then it would be kind of trivial. Yeah, it's trivial when O equals A for that reason. Yeah, everything's symmetric, so obviously KO and KA would be orthogonal. But when O is not A, what's the best way to show it's orthogonal? Maybe projective geometry. Maybe we could show the cross ratio, like FJIG is GIJF or something like that. So if we project those points through K, what would we project it onto? AB, PR. So F and G go to P and R. I and J would go to these 2 points. But I'm not sure how helpful that is. Or we could project it onto AH. I kind of like that better, because then I and J go to O and A, and P and R, we'd have to draw another point here. So yeah, let's draw that. All right. So what was I trying to do? So FJIG, I was projecting it onto AL. And so you'd get OA, L, and T. So if these are isogonal, that means that, I think that means that does that mean that FGJI is FGIJ or something like that? Is it equivalent to like saying L, T, O, and A are harmonic or something?
I don't think it's LTOA harmonic,
Okay.
and I'm not sure if there's something you can do with like switching FGIJ, like switching the order.
Oh, really?
That might work. I don't know.
Because yeah, by reflection, if these really were isogonal, FGJI should be like GFIJ or something, right?
Yeah. But also, I think that's just always true.
That's always true.
I think so, yeah. I think FGJI is always GFIJ. I think you can just switch them.
Hmm. Okay. Maybe we can use the isogonal line lemma somehow. Well, I think it should mean that FG. I was gonna say maybe FGJI is FGIJ, but I don't know. Is that right or no?
If FGJI is FGIJ, then this cost ratio is equal to 1 over itself, because you can just like multiply it out and verify that, and then that would mean it's harmonic,
Okay,
which it isn't.
which it's not. I'll try to use the isogonal line lemma then. So we want to show we have KP, KO, KA, KS. We want to show those are isogonal. So by the isogonal line lemma, we could let PO meet AS at a point. Let's see. And then PA meet OS. Then I think we want to show that those would be isogonal, right? So PO meets AS and PA meets OS. So maybe I could get rid of L after this. So it's equivalent. It's also equivalent to showing KU and KV are isogonal. I don't know if that's any easier, but just thinking about it. Let me check that. Yes. Is KU perpendicular to AS? Let's see. No, it's close, but it's not exactly. Yeah, I don't know if there's really anything special about U. KAS is similar to KOP. Interesting. Whoops. I wonder if there's another way to apply the isogonal line lemma. So I'll just for now draw those, but so SOV and POU. And you were saying that KAS is similar to KOP. Interesting. So yeah, if that's true, that would definitely show they're isogonal. Oops, sorry. KOP, KAS, yes. All right, so yeah, I think that is a step in the right direction. This almost makes it look like AS is parallel to PR, but I'm not sure. I could try it. So yeah, KAS and KOP. Let's see if we can do some kind of angle chase. Is it obvious that any two of them are equal? Or let's see, OPQ. So OPQ. I mean, so that would mean triangles OPQ and ARS are similar. Is that obvious? We want to show OPQ is similar to ARS. Maybe that's just an angle chase. Because okay, so let me delete L for now. Maybe I could also delete U and V. I'm thinking about it. So
Okay, so if you move the circle, I think if you move B, then K always lies on a fixed circle through P and R, which I just found by GeoGebra. But I cannot for the life of me figure out what that circle is supposed to be.
interesting. Okay. So as B moves, K lies on that circle. All right, I'm gonna delete L and all the other stuff I added. That's really interesting. Let's see what time it is. Is C the center of the circle or not necessarily? So, I mean, that would mean angle PKR is 90. So let's check that. That's not true. So yeah, what's another point on the circle? Let's see if we can figure it out. Let's draw the center of it. See what the antipode of K is. Doesn't do much. But yeah, that's definitely really valuable information. So I guess as B approaches O, and this becomes like a point, does that give us any insight? So what would K be in that case? But it's hard to tell like what those tangents are. So well, they would just be the perpendiculars to OP and OR. So you draw the perpendicular from OP at O, and then it would meet the circle at a point Q, and then you'd let RS. So KAS and KOP. So yeah, I like the idea of trying to show those are similar. Okay. Let's see, it's 9:40. We could spend like another 5 minutes and then we could try another problem. So I wonder if POF is KAR. Oops. So we have that. And we have this. No, they're not equal.
Oh, I think I have solved this by angle chasing.
Okay.
So so first we can easily show that the angle OPK is equal to the angle ASK by angle chase.
OPK equals ASK.
Yes, yes.
Okay.
And after that, we will show the ratio PO over PK is SA over SK. Then these two triangles are similar.
All right. All right. So first we do the angle chase to show that OPK is ASK. And you said that's not that hard of an angle chase, right?
Yeah, just a bit of angle chase.
All right.
And we also use the fact that HQAS is cyclic to combine with angle chase to show that those angles are equal.
Okay, so we use that HQAS is cyclic. Okay, so let's see. What if we can? So, all right. So sorry, someone keeps messaging me, so you might keep hearing a sound. Hold on 1 second. I'm sorry, I have to answer this. All right, so sorry about that. Okay, so yeah, my boss is just messaging me. But I told them I'd be back later. So okay, we're using that this is cyclic, and we're showing that angle ASK is KPO. or sorry, it's yeah, was that right? KPO is KSA.
Yes.
Okay. Okay, so KSA is AQP. AQP is APQ. And we want to show APQ. Did I do that right? Wait, so K doesn't lie on this big circle. Sorry, so okay, so how do you do the angle chase?
So the angle OPK is OPR plus KPR,
Okay,
and is equal to the angle OMN plus KPR,
okay,
and KPR is like FSR.
it's FSR.
Yes. So finally, we need to prove that the angle OMN is equal to the angle ASQ.
Wait, so KPR is FSR, because KPR is QPR. Wait, how do you get the KPR is
no,
FS?
that is QSR, not FSR. So.
Okay, QSR. All right.
And so since ASK is ASQ plus QSK, so we need to prove that the angle OMN is equal to ASQ.
Okay. OMN.
But
okay.
But OMN is equal to OHN, which is OHQ, and that is QSA, and that is ASQ.
Okay. All right. So let me write that out. Let me write it on paper first, and then I'll type it up. So we have angle APK is equal.
Oh, that's OPK, not APK.
Sorry, OPK is OPR plus RPK, and which is ORP plus, or that's the same as OMN plus, let's see, RPK is QPK. So that's OMN plus, okay, RPK is QPR, which is QSR. Okay, so we have QSR. OMN is OHM. Okay, so we have OHM plus QSR. Okay, and QSR. So then we want to show that QAS is we want to show that QSA is OHM, and that follows because they're cyclic. Okay, so so that's AHQ QSR, and that would be ASQ plus QSR, which is ASH. Okay, so I'm gonna type it out. So we have, and then we can check it. So whoops, angle OPK equals angle OPR plus angle RPK. Which is equal to angle OMN plus angle QPR, which is equal to angle OMN plus angle QSR, which is equal to angle OHM plus angle QSR, which is equal to angle HQ. Let's see how this turns out. ASQ which is equal to angle ASK. Let me check that this is right. So let's see. Of course we use that this is cyclic, which is important. But okay, OPK is OPR plus RPK, which is OMN plus QSR. And then OMN is OHM, and then OHM is AHQ, which is ASQ. And then, all right, okay, so that's the first part, and then we show and then you said you could show the ratio, right?
Yes.
Okay.
So next, I will show the ratio SA over SK equal to SK over SA is PK over PO.
Okay.
Which is equivalent to, we need to prove that SK over PK is SA over PO.
Okay.
But if you look at the circle with radius AS, then AS which is QS over 2 sine of QAS.
Okay. AS
And
is QS over 2 sine QAS. Okay.
And PO is like the center O with radius OP, so PO is PR over 2 times sine of POR.
PO is PR. Okay.
But from the previous angle chase, it's obvious that the angle QAS is equal to the angle POR.
QAS is equal to POR.
Yes.
Okay.
So we have that SA over PO is like let me see, QS over PR.
Okay, so are you saying triangles POR and QAS are similar?
Yes, because two small angle is equal.
Yeah, okay. So yeah, we don't even really need trigonometry for that, right? So because they're both isosceles and they're both similar. So
Oh yeah, I just forget that fact.
Okay, it's all right.
Yeah, maybe that was faster.
Yeah, that's all right. Okay, so then that would mean that SA over let's see, SA over PO is the ratio of similarity in those triangles, and that would be, want to show that's SK over PK. So how do you, sorry, so let me think about that. How do you get that is
SA over PO is SQ over PR.
SQ
And-
over PR. Yes, that's true.
And it's clear that the triangle KQS is similar to KRP, so we have that ratio.
Because PQRS is cyclic. I see. Interesting. Okay. So, okay. So by an angle chase, POR equals QAS. So by an angle chase, POR equals QAS. QAS, and that means that triangles POR and QAS are similar. Since both are isosceles. And that means that PO over AS equals PR over QS. So PO over AS, PR over QS, which is KP over KS, since PQRS is cyclic. And so that means that KPO is similar to KSA. That thing keeps popping up now. I don't know why. And that means that KO and KA are orthogonal in PKS. Or I'll say angle PKS. And that means that KJ is an altitude of KFG, since KFAG is cyclic. So I'll say KFAG is cyclic by right angles. So KFAG cyclic by right angles implies that KO is an altitude KFG, since KA is a diameter. And that solves the problem. FG is perpendicular to OK. All right, this is a great solution. Thanks a lot. So yeah, nothing super fancy in this, but yeah, that angle chase right here was key. That really helped solve it. All right, so I'll move on to the next one. Yeah, I'm glad we were able to solve that. 11, there we go. So we have a triangle ABC, and then we draw the circumcircle and a 9-point circle. I think I might already have a tool for the 9-point circle. So there we go. And you draw the circumcircle. The orthocenter, let's just do this. All right, This is H. I don't know why H didn't show up, but so it's saying it's saying it wants like A1, B1, and C1, I think, to be the altitudes. So let's do that. D, E, F would be the midpoints. And then, okay, D. So it's saying A, B, C, A, and B, C. That's a little weird, but okay. So DH, if we extend DH beyond H, it intersects the circle at D1. So, and then we would draw E1 and F1. Okay, so D1, E1, and F1. E1, and this would be F1. And then we want to show D1C, E1B, and AA1 are concurrent. So we don't even really need F1, right? We can kind of delete that, I think. So D1C and E1B. Meet on altitude. This doesn't look like it should be that hard of a problem. It's hard to say for sure, but it doesn't feel like it should be that hard. So let's see. All right. So yeah, I mean, we want to show those concur. Is that just, so is this a right angle right here? H D1C? It almost looks like it, but I'm not sure. Oh yeah, then it would be just the orthocent. Then it would just be true by the radical axis theorem if that were the case. So that, yeah, I mean, that would, then the problem would be trivial. We'd just have to show that's a right angle. And is that obvious? So yeah, then I don't even really need to draw any of these really. All I need to show is hide this, delete that, delete these two. Yeah, so this might just be a really easy problem then. You just have to show that this is a right angle right here, and that it's true by the radical axis theorem.
And I mean, that's just true because if you draw the diametrically opposite point to C, and then that lies on DH, that's just the other point on DH.
Okay, so if you draw the point diametrically opposite of C, you said?
Yeah, for example. Or of B, it doesn't really matter.
Okay. Then that point so basically that point's concurrent with D and H is what you're saying, right?
Yeah.
That's a well-known fact. So so basically CH, these would all be collinear. And so so it's a right angle. Yeah, so this problem's trivial. Yeah. So yeah, power of point, radical axis theorem, it's kind of the same idea. Okay, so I'll just write it up super quick. But yeah, a lot easier than the last problem. Let C prime be the antipode C. then it's well known that HD and C prime are collinear. So that means angle HD1C is 90. So HD1CA1 is cyclic. Similarly, HE1BA1 is cyclic. So by the radical axis theorem, those concur. I don't know why this keeps popping up. I don't think I've had that happen before. E1C, E1B, and AA1. All right, let's move on to the next problem. This is easy. Let's see this one. This one looks kind of interesting. So we have a triangle ABC, and we draw the in-circle and the in-center and the x-center. So let me see if I have a tool for this. Okay. Let's see how this comes out. Oh, yeah, sometimes when you have like points of tangency, yeah, I should have, I think you even mentioned I should have drawn it like a different way so that the point always shows up. But let's see who's on. Okay, looks like on either lost connection or how to leave. Okay. So let's draw the circumcircle. So I'm going to want to relabel things. So this is I, and then we draw D, E, and F, and then we draw the in-center. I'm sorry, the x-center. So IA is this point. Let's rename these. D, E, and F. And then we draw the circumcircle, so it's centered at this point M. So by the in-center, x-center lemma, this will pass through IA and it's centered at M. And they call M and N two different things. So this looks like a good opportunity for root BC inversion, maybe something like that. So we have M and N are where this circle meets the in-circle. So either normal inversion or root BC inversion looks like a good choice for this problem. So FM intersect ND, and FN. So FM intersect ND. We want to show that lies on. Doesn't look right. And FN intersect DM. So those 2 points.
I think they just mean one of them,
Okay,
but
but even that's
wait.
not true. Let me check FN intersect TM. Let's see, did I do something wrong here? I, B, the incenter. D, E, and F are the altitudes from I. So we draw the circle. Those intersect at M and N. M is nearer to B. That's true. And FM intersect MD. And FN intersect MD. So I think the original problem didn't have like the circumcircle notation. So let's see. Here is the original problem. Lies on IAB. Okay, that's where I messed up. Okay, so this should be, the problem should really be dang it. Okay, so let me maximize and fix this. Okay, so it's really like this. IAB and CIA. All right. So yeah, it's really to show that both of the points lie on that. Okay. All right, so I'll delete this circle. Let me hide a couple things so it doesn't look so bad. It's probably a similar proof for one versus the other, I'm assuming.
So the fact that they both lie on, or that the 2 points and B are collinear, so H, J, and B is pretty easy by Brocard's theorem. Because if we draw the intersection of FD with MN, we know that both H and J lie on the polar of it with respect to the incircle. But since that point lies on the polar of B, because that is the polar of B is just FD, we know that B also lies on that polar.
Okay. So by Brocard's theorem, we can easily show that H, B, and J are collinear. All right. So, and then we want to show that line passes through IA. So it's the same as showing that but we know that's a right angle, so I think it's obvious, right? Because IA is 90, and it's like a well-known fact that like it's well known that I, K, and B are collinear and make a right angle, right? So
What is that?
So yeah, whenever you have a cyclic quadrilateral and you apply Brocard's like this, it turns out that the line connecting the center of the circle to the intersection of the diagonals is perpendicular. Well,
yeah, but why is that B?
Why is it B? So
Oh,
angle IBIA is 90 degrees.
yeah, I think I get what you mean.
And so actually let's think about that. So yeah, IB is perpendicular to HJ and IBIA is 90. So if you combine those two, that proves it, right?
Wait, no,
yeah.
how do we know that I, K, B are collinear?
I think
Is that just like a well-known fact, or?
I think think it's a well-known fact that the what do you call this point? The McKell point. I think it's well known that IK passes through like the McKell point of the quadrilateral. So like B
Yeah.
is the McKell point. I think I've used.
Why?
Yeah. Let me think about it. I think I've used it on my channel a couple times, but I think it has something to do. Trying to remember the proof.
So is that like something? Are you using something specific to the points M and N? Because I don't think it works if you don't.
So like if you have any cyclic quadrilateral, and you just use Brocard's theorem,
Yeah, I agree that IK is perpendicular to HJ, but how do we know that IK and B are collinear?
okay. So yeah, I see what you're saying. So I think it's always true that the IK intersects the polar at the McKell point.
Yeah.
So we have to show B is the McKell point of let me think about this. The McKell point of that quadrilateral. So is JBFN cyclic? So yeah, let's see if we could show that B is the McKell point of that quadrilateral. You can prove it by angle chase. Let's see. So it's kind of the same as showing that FD is parallel to JH, I think, right? Because angle NFD is N.
Yeah, just because they're both perpendicular to BI. Or one of them is and one of them is supposed to be.
Yeah. Well, okay, we know FD is perpendicular to BI. And yeah, we want to show JH is perpendicular to BI. Okay. But Pascal, you said we can do it by an angle chase?
But I'm still figuring out like the different way because the one I have learned is it's a bit ugly and a bit long,
Okay.
like a bunch of angle chase.
All right.
Oh, I think I have like a proof. We know that MIA and NIA are tangents because IIA is the diameter of that circle, so that's right angles. They're tangents to the small circle. So this point K just also lies on the polar of IA.
Okay.
Because
so
that's
K,
MN.
So K lies on the polar of IA, and so that means, let's see. So then where do you go from there?
I prove that MIA is a tangent to this to the end circle. And so is NIA.
Oh, since IA lies on the polar of K and we already knew this was the polar of K, then they're all collinear.
Yeah.
I like it. All right. So, all right. So I'll just say label the points as shown. So by Brocard's theorem, Hj is the polar of K. And then we know that B lies on the polar of K, since BF and BD are tangent to the circle. So K lies on the polar of B, implies B lies on the polar of K. Okay. And then angle IAMI is 90. What did I do wrong here? B, gotta get rid of that one. Okay. So we have angle IAMI is 90. So implies, so that means IAM and IAN are tangent to the circle, and that means that that means that K lies on the polar of IA. And that means that IA lies on the polar of K. Okay. And that means that K, H, B, J, and IA are collinear on the polar of K. Polar of K. Which solves the problem. And similarly for the other part. All right. So that was easy. Let's move on to the next part. Okay, so yeah, these problems were from the marathon. I'm not sure how hard they are. Let's just look at it really quick. So you have a point on the angle bisector, and M is the midpoint. Let's draw the bisector. And J lies on it. And then we draw the pedal triangle of J. So let's draw perpendiculars to each side. It's X, Y, Z. Yeah, they don't tell you which is X and which is Y and which is Z. So I'll have to guess here, but assume it would be like this. XJ.
Yeah. If you like this is like a generalization of a well-known lemma where like if J is the incenter, this is well known, and
Yeah.
they've generalized it. So this ordering makes sense as well.
So XJ. Yeah, so I wonder if this is just like a homothency, the more generalized lemma. It kind of looks like it, because if you take the incenter,
Oh yeah.
is it? Yeah.
Yeah, it's just true. Like if you I mean you can basically draw arbitrary parallels to BC.
Yeah.
And like yeah. If you
It's
just draw the circle through J with midpoint J through Y and Z, and then take the bottom tangent of that one, then like M will lie on that. Or the midpoint of that will lie on AM. And then it's the lemma.
okay. So it's just the homothety. Well, let's think about it. So we want to show those figures are homothetic. So we're saying because AZJY is homothetic to AEDF, then A, K, and H are collinear, and it's well known that AH and M are collinear. So yeah, that's too easy. All right, so I'm not even gonna write that up. Let's see if we have a harder problem.